The today's session is mostly on the laser heating, and the main crux in it is a moving heat source. So the title itself clarifies both things, modeling and simulation. I'm not only focusing on how to simulate the process, but modeling itself is saying if you understand how it is built theoretically and numerically, in future even you can build your own thought process. So this laser assisted machining, whatever heat source I am going to show you, you can use in many applications. It's not just limited to laser assisted machining. Any moving heat source, let's say if you see arc welding process or any kind of arc cutting process, wherever you see a heat source, either stationary or moving. Moving is one step ahead anyhow. So you can simulate a stationary heat source, moving heat source in various applications. So from that point of view, I am using the word modeling. And simulation is something, once you have your thought process clear on the pen and paper, theoretically, then you can simulate in any software. It's not just Abaqus or something. That is just a solver kind of thing. So broadly, you should understand, as I told you, the background of whole course, what it contains. Broadly, it contains laser assisted machining, like this. So machining is one thing, conventionally everybody knows. Machining involves a cutting tool, workpiece. One cutting tool moves and it will remove the unwanted material in the form of chip. That is the conventional understanding of machining. But if you have additionally laser in it, let's say laser heating is there. So I just shown laser as a dot here. So imagine if laser in front of your tool is hitting the workpiece and it's moving with the same velocity as the cutting tool is moving. Let's say laser is moving in this direction, your cutting tool is also moving in this direction with same velocity. What will happen? The laser heat source will heat the surface of the workpiece, and this heat will conduct inside the workpiece up to some depth. So certain depth of the workpiece will heat up, the temperature will increase, and that will cause a very simple physical phenomenon that everybody knows, that is thermal softening. So most of the metals or most of the materials, I can generalize it, except few polymers. So generally, when we heat up, the material gets softened. And exactly that will happen here. So laser concentrated heat, laser is a concentrated heat source. So locally, high amount of heat will be generated, and due to material conduction and convection, it will slightly spread out. So some amount of width and depth of the workpiece get thermally softened, and exactly that thermal softened layer will remove. Let's say this is the thermal softened layer after laser heating. So that thermally softened layer will remove with the cutting tool. So what is basic understanding? Compared to hard surface, now cutting tool is going to remove the softer part. So definitely the cutting force requirement will go down. And the cutting force requirement will go down means the cutting tool experiences lower cutting forces. That will finally, economical advantage is that the cutting tool wear will reduce. The cutting tool will last, means it will give more tool life. The more correct word is the tool life. So it will improve tool life. At the same time, due to lower cutting forces, your surface finish will be better. Your process will be much smoother, and you do not require very high rigid machine tool and the very rigid fixtures and clamps. So there are many advantages we are getting with the laser assistance. That's why the focus of this session is understanding of laser heating, and with the laser heating, understanding of thermal softening. So one by one, now we'll start. So how laser look like basically? So now one more important aspect. If laser heat source is moving, it can move in any path. Again, user will decide what kind of scanning path he wants. The most famous is definitely a straight or linear path. But again, mathematically also and even practically also, sometimes it is feasible or required to move your laser in a certain path. Let's say I have shown here sinusoidal path. Someone may say, can we move, let's say, like a cycloidal path, or let's say elliptical path like this? Yes, possible. And even in the same subroutine it is possible. Again, you need to change your equations and just customize your subroutine. As for linear path, it is very straightforward, because as I shown here coordinate system, you can see here the x is along the scanning path. So our laser have only one velocity. So just surface heat flux as I see here. But due to heat transfer phenomenon, heat may transfer in the width direction or in the depth direction. Convection is possible, radiation is possible, and this is a very high temperature laser beam. Or ambient temperature is always available, so convection is also possible. So all three modes of heat transfer will be active as your moving heat source is there. So for accurate modeling, I should consider this 3D heat equation, so that my temperature is a function of, and that too transient, it's not a steady state. So my temperature will be function of x, y, z and time. Because it is moving, the whole process is dynamic. With the time, so as I told you, I will show you two things or two kind of subroutine, let's say. The purpose is same, to model moving heat source. But in Abaqus, there are two main solvers are there. Abaqus standard, which work with implicit method, and Abaqus explicit. The name itself suggests that works with the explicit method. So this what are the advantages of two solver, when to use which solver, and that is a separate topic actually. We will not go in that much detail. But in our context, I will tell you. Whenever a model consists or simulation consists lot of non-linearities, dynamic phenomenon, contacts, damage, such kind of complex things, it's very difficult to handle with the implicit algorithm. And mostly such kind of very fast wave propagation phenomenon involving material non-linearity and the contact non-linearity, engineers, scientists prefer explicit method because that will converge your solution. So for this session, we are only talking about heating. That's why both is fine. I can do heat transfer simulation either with implicit method, explicit method, because this is very simple simulation. We'll get good results with any of the method. But when we'll go for the machining simulation or laser assisted machining, that time all the non-linearities will come into picture. And that file previously, and I have results available. If I will visualize it, results, you can see. I will show you first video. how my moving heat source we can see. See, the laser beam is moving and it is conducting heat. From top view I am showing. I will show you cut view also. Okay. The Y direction I will take cut. And I will show in the thickness direction. See the conduction, one can easily see. I will go frame by frame. As laser source is moving, the heat is conducting downside. At the same time towards width. In all direction, X, Y, Z, because temperature is now function of X, Y, Z and T. Time also. So in latter part, the same softened zone we will remove through the cutting tool, using cutting tool. So that will make our laser assisted motion. And the results also even we can verify. I will show you quickly. Okay, we'll go in default orientation. See, let's say after 5 seconds, what are the results? I can choose frame number here. Here you can see time. So if I will go slowly, the 0.49. Okay. So this limits I will take default auto. Okay. Anyhow it is auto. So the maximum temperature is showing here 2.214 10 to the power 3 means 2214 degrees Celsius. After let's say 0.4950 or 0.5 second. This is how we can analyze the result, we can plot the result. We'll see in literature what they are saying. In the same paper, they also perform this simulation. Here you can see. Maybe in different software using different method, but still we can validate our results. Because whatever physics we are following, that is perfectly in line with the practical laser heating. So it doesn't matter whether in literature this simulation is performed in some other software, ANSYS or console, or people use analytical method, or some did see how the laser path scanning. Because in our future simulation, it is followed by our cutting tool. The same laser beam will be followed by cutting tool. So this softened region from width wise or depth wise will be removed by the cutting tool. So this is the linear scanning path. Sinusoidal I will show you. Whole methodology will be similar. Only the subroutine will be our sinusoidal subroutine. Okay. So I will play video first so that you can understand. See how the laser beam will travel. It is like a sine or cosine path. Right? At any point of time, we can check temperature. Let's say I will check my temperature on some of the peak. Let's say I will go at this peak, let's say, okay, where a reversal will start. Okay, temperature is almost, I will keep what is the maximum temperature I can see. I will check. So that is 2059. It is almost stabilized, I think.